So let's consider the integral of the sine to the 5th power of x over 3 times the cosine of x over 3 with respect to x. And so it's kind of a complicated integrand, and so we'll need to consider a substitution to try and simplify it. Suggestions? So if we just go with x over 3, the problem here is we have that product. And if you remember the product rule from calculus, if you take the derivative with respect to x of two functions u, v, then you get u prime v plus u v prime. And this does not have a sum in it. So we have a problem with that product right here. So just letting the substitution be x over 3 won't be enough. So here's a hint. I could remove the 5 from there and write it like that. That's what the 5th power of the sine really means. So here we have a function within a function within a function. So we could try just using x over 3 and we'll find that sufficient. So usually the next step is get something a little bit more. So let's try using the sine of x over 3. Okay. So if I let u equal the sine of x over 3, what will du be equal to? Derivative sine is cosine. And then this is a function within a function, so we have to adjust by multiplying by the derivative of the inner function. Derivative of x over 3 is 1/3, and then the dx goes here. And so now the cool thing about picking that particular u is I can see most of it lives in there. The only thing I'm missing is the 1/3. But a multiple of something is super easy. You can just throw that in. So I could just multiply in a 1/3 right here. To compensate, I'd have to also multiply by 3, right? Because 3 times 1/3 is 1. Doesn't really change anything. The benefit of doing that is I now have that whole du up there. So my claim is I can rewrite the blue integral as 3 times the integral of u to the 5th du. And that's what we want to have happen. We want that extra stuff to kind of collapse into that du, right? And that's the application of the chain rule in reverse. And we can totally handle this. Antiderivative here is going to be 3 times u to the what? 6th, yeah. And then we divide by 6 because we're reversing this. And then because we don't have boundaries on the integration, we have to say this could be plus some constant. So we put a plus c over there. And then we reverse substitute back. So we say, all right, u is really equal to the sine of x over 3. So I got to throw that in place of u. So rewriting it, we get, and let's see, 3 over 6, I can clean up that too. That's going to be a 1/2. So I'm going to say this is 1/2 times the sine to the 6th power of x over 3, and then plus c. Could we have made a mistake there? We're too good. I make mistakes all the time, so I'm going to check. Now, I'm pretty good at differentiation, right, because we just spent a whole term on that. So I'm just going to take the derivative of this blue thing and see if it gets back to what I wanted. That doesn't matter, because if it's some constant you don't know and you take 3 times it, you know, have 3 times the constant you don't know, which is still some constant we don't know. So we don't even worry about that. Yeah. So we can just call it C. All right, so just to double check this, I'm going to take the derivative. So this is a check. I'm pretty sure that's my antiderivative, my indefinite integral. So checking this, oops, we just want to say, okay, what's the derivative with respect to x of this thing here? 1/2 sine to the 6th of x over 3 plus c. Now the plus c is easy, derivative of a constant, 0, that's going to go away. But this thing is more complicated because I have actually 3 functions living here. I have the 6th power, right? That's a function. The sine's another function, and the x over 3 is a third function. So I have to apply the chain rule 3 times in a row. The thing I have to do here is identify the outer function. So which is the outer function here, and which is the innermost function here? The 6th power is the outermost, correct? Yeah, and I always, whenever I'm stuck, I think about order of operations. If I plugged in a number for x, what would be the last thing I did? So if I plugged in a number for x, I'd first divide it by 3, then I would find the sign of it, and then I'd raise it to the 6th power. So the chain rule has to start with the 6th power. So the derivative here, the 1/2 is just hanging out front. Derivative of something to the 6th is going to be 6 times whatever the base was, and then we reduce that power by 1, right? So that's the power rule on that base. The chain rule says you got to multiply by the derivative of the base, okay? The derivative of the base, well, the base is the sine, so that would be the cosine. The x over 3 is still trapped inside, right? And then the chain rule says one more time, there's an inner function multiplied by a third, and I'm running out of room, so I'm going to write that out front. So there's the chain rule for a function within a function within a function. And then we clean it up and hope it matches what we started with. So let's see, what do we got? 1/3 times a half times a 6, that's 1. So that's kind of cool. So it looks like this simplifies to be the sine to the 5th power of x over 3 times the cosine of x over 3, which is indeed what we started with. So when you're ever in any doubt, and the homework gets us kind of lazy because it's got that check your answer button, right? On a test, we don't have a check our answer button. We are the check our answer button. And so a super big tool is using what we know about derivatives to confirm we have a correct antiderivative. Or if it was numerical, whip out something like GeoGebra to double check it numerically. But here, GeoGebra won't help. All right, so that looks pretty good. Let's try another one. How about, ooh, I'm gonna pick that one because my first glance at it, I have no idea how to do it. That's always gonna be exciting. All right, so the integral of, let's see, do I have this right? The square root of x minus 1 over x to the 5th with respect to x. Interesting. So we just try something, see what happens. Any thoughts? We got to pick something for you to try and make this simpler. Say that again. Oh, so let u be the whole inside? Okay, let's try that. So let's let u equal x minus 1 over x to the 5th. To take that derivative, we have 2 options. We could clean it up algebraically first, or we could apply the quotient rule. What do you want to do? Okay, so quotient rule for du says take the derivative of the top, that's 1, multiply by the bottom function, minus the top function times the derivative of the bottom function, all divided by, anybody remember? Isn't it the square? I guess I haven't done that in a while. Yeah, denominator squared. So x to the 5th to the 10th. Sorry, I said the answer. X to the 5th to the 2nd would be x to the 10th. Yeah, we square that denominator. And then we clean that up. So we have an x to the 5th, and we have to do a bit of distribution here, and the negative gets distributed. So we could say we're distributing a negative 5x to the 4th here. So that'll be a negative 5x to the 5th. Negative would be a plus 5x to the 4th. Which equals what? Negative 4x to the 5th plus 5x to the 4th. And we can factor out an x to the 4th from the top. Oops. So we could say this is x to the 4th times negative 4x plus 1. And that'll cancel with part of the x to the 10th. So it looks like we have negative 4x plus 1 over x to the 6th. And the whole time here, we should have had a dx hanging out at the end here. Okay, so do we see that sucker sitting outside of the square root? Is that up here? Answer is no. So that means this, at first glance, is not a productive u and du. So we got to try something else. So one thought I had on this was I usually like to avoid the quotient rule. And so I was thinking, let's rewrite this algebraically. So I'm going to try that over here. I'm going to switch colors. And I'm not going to erase that. Just I might be able to use it later. It just doesn't look like it's going to work right now. So I could view that as x over x to the 5th minus 1 over x to the 5th. Maybe this will help. So what would that give me? That would give me 1 over x to the 4th minus 1 over x to the 5th. All that is trapped inside of the root. Everything's being divided by x to the 5th here, both parts up there. Well, that doesn't look like it's going to help much either. Okay. So we have the integral of, oh, that might help. So as the 1/2 power, right? So we could say that's x minus 1 over x to the 5th to the power 1/2 with respect to x. Not sure what to do yet. Let's see, what else could we do here?
What happens when you distribute the power through everything?
There's a catch there, and the catch is this, that if you have something like the square root of a over b inside, that's equal to the square root of a over the square root of b if a is greater than or equal to 0 and b is greater than 0. They both have to be positive for that to work. So we could make the condition that that has to be true. So if we go back here, we would want both the x minus 1 to be greater than 0 and the x to the 5th to be greater than 0. So our a was x minus 1. If that has to be greater than or equal to 0, then that would imply that x has to be greater than or equal to 1. So if we stick with that condition, then we could rewrite it as, the square root of x minus 1 over the square root of x to the 5th. And that could be rewritten further, right? Because x to the 5th could be thought of as x to the 4th times x. And so then we could say this is the square root of x minus 1. I'm not sure if this is going to help. The square root of x to the 4th is x squared times the square root of x. Ooh, that's got an idea. That gives me an idea right there. If we, oh, maybe not. So let's see, new page. So we have the square root of x minus 1 over x to the 5th, right? Which could be thought of as the square root of 1 over x to the 5th times x minus 1, which if x is greater than 1 or greater than or equal to 1, then we could separate that as the square root of 1 over x to the 5th times the square root of x minus 1. Mm-hmm. On which part? Oh, take the derivative of this whole thing. Well, that won't help because this is the same thing we were trying to take the integral of in the first place. So taking the derivative of the whole thing is not going to help. We have to take the derivative of just part of it for substitution. And so the key is whenever we pick something for u, somewhere in what we have, we're looking for a du there also. Like think back to that original problem we did over here. We picked the sign as the u, and the main reason I was thinking that is because I know the derivative of the sign is the cosine. So I'm seeing du in there. So whenever we pick a substitution, we're hoping that whatever shows up here is also in here too. And again, the chain rule says it's always going to be a multiple. So that's one reason I was thinking that we should break up things as multiples of each other. Let's go back here for a sec. With this right here, we could rewrite that as x to the negative 4 minus x to the negative 5th. And we have a rule that says we can factor out the lowest power that they have in common. So here the lowest power was x to the 4th. Here the lowest power would be that'll just take us back to where we started, darn it. If we factored out a negative x to the 5th, we would get x to the negative 5th times x minus 1, which we had on that other screen. We could, but I don't think that will help, but let's try it. So let's get a clean slate here. So again, we have the integral of the square root of x minus 1 over x to the 5th. And so you're thinking back to this version of it that we could say it's the square root of 1 over x to the 4th minus 1 over x to the 5th. In the negative format, yeah. So again, that'd be the same thing as the square root of x to the negative 4th minus x to the negative 5th. Oops, dx. Okay, let's try it. So if we let u equal x to the negative 4th, then du, we drop the power by 1, which gives us, we bring the power down, negative 4, and then x to the negative 5 dx. And the thing is, this has to be a multiple of something over here. But the x to the negative fifth is not a multiple of this over here, is the problem. Hi, Gerald. We're playing around. It's got to be an integer multiple. Or no, it doesn't have to be an integer multiple. It just has to be a constant multiple. Yeah, so any constant multiple is okay here, provided the x to the fifth is a multiple of the whole thing over here. And we don't have that. So for example, right now, we could come over here and say that this right there, that's u. But the dx is outside of the square root. And the x to the negative fifth is inside the square root. They're not directly connected by multiplication there. So that's a problem. So we can't fit that in as a substitution. Yeah, there's only one dx. And you can't have dx's and du's floating around at the same time, at least not in what we're doing as single variable calculus. Next year, you can do multiple variable. All right, so we'll come back to this one later. I'll think about it. Let's try another one. So we got to, no, not yet, not yet. It's too soon. Usually I don't go to Wolfram if I can't solve it in a day. Then I'll go to Wolfram. All right, so we'll try another one. We'll come back to that one another day. Let's see what else. Yeah, so I picked that one because I looked at it and I was like, I don't know how to do that off the top of my head. I don't remember if I put that one in the homework. Yeah. All right, so let's try this one. Let's take the integral of x cubed times the square root of x squared plus 1. Actually, this one looks like it might be equally hard. All right, so we have to come up with a u here to try and simplify it. So first guess is at a u. The whole square root. So that might be too much, but we could take a look. So if we let u equal the whole square root of x squared plus 1, I would probably rewrite that as x squared plus 1 to the 1/2, unless you remember the derivative of a root. So for example, my recollection is the derivative of the root is 1 over twice whatever was in the root, which you get out of that one right there. There's an x squared plus 1 in there. Then I have to multiply the by the derivative of the inside according to the chain rule with it, which is an x squared plus 1, which is 2x, yeah, sorry, dx. So the problem is since we picked this as the u, I'm hoping to see du in the remaining parts. And this is my du. So this choice of u doesn't look productive because the remaining pieces don't represent it. So let's try another. What if we just tried letting u be the inside of the root? U equals x squared plus 1. Then du is just, what, 2x dx. And I can fake a 2 in there, all right, but I still have extra stuff. But I think there might be a way around it. Let's try it. So let's see. I'm going to rewrite this for a second. If there's a 2 right here, so it'd be nice if there was a 2 over here. which means I'll have to compensate by putting a 1/2 outside. Out of the x cubed, I'm going to pull an x to go with the dx, which is going to leave an x squared outside. So I'm going to rewrite it like that. If I do that, then I can say, well, I have for sure the square root of u, right? And then x dx, well, that's my, I put a 1/2 there. I should put a 2 in here to compensate. So the 2x dx is my du. At the moment, though, I still have a slight problem because I still have that x squared hanging out here waiting for something to do. So I need to replace that x squared with something to do with u. Well, if I look at this guy right here, I could rewrite that and say, if I take the 1 to the other side, then x squared is equal to u minus 1. So I could try putting that here and see what happens. So that would be a u minus 1 times the square root of u du. We still got the 1/2 out front. And this isn't too bad because that's just u to the 1/2, right? And couldn't I just distribute that through here? So then what it looks like I have is a 1/2 times the integral of, let's see, that's u to the first, 1 plus a half would be u to the 3/2 minus u to the 1/2. And this is nice because I can integrate across a sum or a difference. So I can go right through that. So what happened here is we took the sum which was inside the root, which was a problem, and this twisted version of the substitution allowed us to take and put it as a difference outside. And now I can use what's called the linearity of the integral, meaning I can move the integral through a difference to solve this. So it looks like I have the antiderivative for x to the u to the 3/2 would be what? Nope. You add 1 to the power. So 3/2, add 1 to that would give me 5/2. So I'd have u to the 5/2 divided by 5/2, or you could say times 2/5, minus increasing 1/2 by 1 is going to give me a u to the 3/2. And then what, times 2/3? And does that clean up much? I could factor out a u to the 3/2, but I don't think that makes it any prettier. I think I'm just ready to reverse substitute. So reverse substituting u equals x squared plus 1 and multiplying the half through here, it looks like an antiderivative is 1/2 times 2/5 would be what, 1/5? And then u is really x squared plus 1 to the 5/2 minus 2/3 times a half would be 1/3 x squared plus 1 to the 3/2. And then all along we should put a plus c at the end because we're not evaluating endpoints. So I think we have an antiderivative for our original function. Yeah, so the trick with picking a substitution is not picking too much and not picking too little. And sometimes you also have to, it's not just a straight substitution, you can do some fiddling algebraically, right? So we are missing, like on this problem over here, there's some little algebraic fiddling we need to do that we haven't thought of yet that will make a substitution work on that one. So we'll look at that later. All right, let's try another one. How about, ooh, that's an interesting one. The integral of the cosine of x times e to the power sine of x dx. So what looks promising here? Yeah. Yeah, so I think you're saying, so that if I take the derivative with respect to x of something like e to the u, the derivative will be e to the u times u prime, which is precisely what I have here, right? Derivative of the sine is the cosine. So then I think we should let u be the sine of x, because then what will du be? Cosine of x, yeah, dx. And so I can rewrite this then as this cosine of x dx is my du, and then e to the sine of x is now e to the u. And since the derivative of e to the x is e to the x, the antiderivative here is just e to the u. And then we have plus c. So reverse substituting, e to the sine of x, and then plus c would be a general antiderivative, which is also called an indefinite integral. I know, yeah, it's that's the interesting thing about the substitution. Sometimes they go well, sometimes it takes a few tries to get one that works, and usually you have to intervene with some algebra. Say that again? Yeah, yeah. And just double checking, if we take the derivative of that, we know the derivative of a constant is 0, so we can pretty much ignore that. And then we know the derivative of e to the something is e to the something. And the chain rule says you then need to multiply that by the derivative of the inner function. Derivative of the inner function is the cosine of x. And so we match. Yeah. Yeah, and here we have, actually, we don't even have any numbers at the moment. We took here we're taking the numbers out of math. Never mind putting letters in. All right. Let's see. Ooh, that one looks nasty. I don't think we'll do that one right now. All right, you asked for it. The integral of 1 over the square root of x times e to the negative square root of x times the secant squared of e to the square root of x plus 1. You do? Oh, good. All right. I think I copied that right. What inverse function are you thinking of? Yeah, so we don't actually have any inverse functions here. So like secant inverse or anything like that. We just have the secant squared. But notice we do have a multiple of the secant squared here, right? So what we could do is hope that that multiple outside here is going to be my du. Secant is 1 over cosine, correct. I would avoid, so I have two thoughts on that. So sometimes I do rewrite secants and cosecants as sines and cosines, even tangent, and a lot of times that helps. Here, I think that's going to throw an extra complication because we'll get a 1 over the cosine squared. But here's a thought that might help us here. the derivative with respect to x of the tangent is what? It's the secant squared, yeah. So if somebody said, you know, I need you to integrate secant squared of x, I can say, oh, that's just the tangent, right? So if I just had the secant of u, then I get this thing nailed. So that means I think I want to try and get this out of the way there. All right, so I'm going to let my substitution, I'm going to try this first. I'm going to let u equal e to the square root of x plus 1. So let's see, what would du be then? I'm hoping du is the stuff I highlighted up above. So the derivative of e to the square root of x is going to be e to the square root of x times the derivative of the square root of x, which is 1 over twice the square root of x. Keeping that in mind, if I look above here, well, here's 1 over the square root of x, right? So I got that. A constant multiple is no big deal. I can always adjust that in. And then check this out. If I have an e to the negative square root of x on the bottom, what does that negative exponent tell me to do? Put it on the top, yeah. So, and that's what I have right here. That is on the top right there. Oops, I forgot to write my dx. So, because what I have here is I have e to the square root of x over twice the square root of x. And this negative right here is saying, hey, you can put that in the top to make it a positive. So I almost have du. The only thing missing up here is a multiple of 2 in the bottom. So I compensate, right? That's really a 1/2. So I compensate by multiplying by 2 on the outside to get this guy right here in there. So I think what we have now is twice the integral. This whole thing now is my du. And then I have the secant squared of u. Right? Because this right here is the same as that right there. Yeah, I think we nailed this. So I am, yeah, this makes me feel better after failing to solve that other one. So here we looks like we have twice the tangent of u, and then plus the constant. And then we back substitute. So we think a general antiderivative here is twice the tangent of e to the square root of x plus 1, close parentheses, and then plus c. And we could check that by taking the derivative of this right here and showing that we get that blue stuff above. All right, and I'm about out of time for playing with derivatives right now. I got another class to get to. So thanks for playing. It's always fun. So bonus if you come up with an antiderivative for this guy right here before I do without using Wolfram alpha. What's that? Without, no Wolfram alpha. Yeah, try to solve this without Wolfram alpha. Yeah, so play around with some algebra. Okay, yeah, so play around with it. Yeah, so usually with something like that, I give it a day before I consult Wolfram alpha for a hint. You can do anything you want. All right, uh-oh, what happened to my recording? Oh, there it is. All right, so I'm going to tie this up now. So if anybody out there in internet land has any questions, feel free to email me. I'm going to sign out now. Bye, Gerald.